In this video, we're going to take a look at the special theory of relativity, and of course, the very famous equation E equals mc squared. Key ideas about special relativity, including the connection between the relativity that we experience every day and also how we connect to mass energy equivalence. So here's a look at the relativity that we experience every day. Let's imagine for a second that we have a game of pitch and catch going on the back of a flatbed truck, with the truck parked, no velocity, no acceleration. And we have two observers. We have the catcher, who's going to time how long the ball takes to go from the pitcher to the catcher, and then we're also going to have an umpire who's watching as well. So if the truck is moving with a constant velocity, then we can start to see how the two frames of reference are going to differ. So the catcher is moving along with the truck and sees the distance the ball travels to be the speed of the ball times the time it takes to travel from the pitcher to the catcher. And then we also have, in the umpire's frame of reference, which is not moving, we have an additional distance that the ball travels, which is the speed of the truck times the time of the pitch. So in this table, we can see what's relative and what's not. So the catcher and the umpire will disagree about distance and velocity because they're relative to their frame of reference, but they'll agree on time, and this concept is called simultaneity. While we're at it, we could let the truck accelerate, and we could see that when the truck accelerates, it's going to actually, to the catcher, look like the ball slows down. And this makes that frame of reference a non-inertial frame of reference because it's going to look like there's a force acting on the ball, but there's not. So now if we take a look at what happens with relativity when we consider reference frames that are accelerating. In this case, imagine we have a projectile launcher that's going to shoot a ball across the spaceship. And if this ball is, if the reference frame is accelerating, then the ball is going to experience a vertical displacement that's equal to -1/2 at squared. But also, if the spaceship is sitting in the presence of a gravitational field, then the ball is also going to experience a deflection, and that deflection is equal to -1/2 gt squared, where g is the value of the gravitational field at the surface of this planet. So it turns out that this is something that is suggested of general relativity, is that you can't tell the difference between being in a gravitational field or being in a frame of reference that's accelerating. So we can see that gravitation warps the local space-time continuum. And there's evidence of this. So as a part of this, Einstein predicted that if you were to make an observation of a star during an eclipse, in an eclipse, a total eclipse, so that the light of the sun is blocked out by the moon and that you can see stars during the daytime, predicted that you would actually be able to see, you could observe a star at a different apparent location than it really is. That the gravitational well of the sun creates sort of a lensing effect that's going to bend the path of light. And this was experimentally determined. So it does leave us to an idea about, is there an ultimate rest frame? And the answer is yes, of the deep starry background. If we, if you can imagine a fighter jet that launches a rocket, the rocket's going to have its own acceleration, but it's also going to benefit from the initial velocity of the fighter jet. And so the speed of the rocket would be its own speed plus the speed of the fighter jet. But it doesn't work in the case of light. So many experiments have gone into trying to show that light the speed of light depends on the frame of reference, but they've all been inconclusive, or they've all failed, really. And so we have to take as fact that the speed of light is always constant, regardless of your frame of reference. So now let's go back and take a look at our flatbed trailer conversation. And now there's a pulse of light that's traveling from the pitcher to the catcher. Because everybody has to agree on the speed of light, now velocity is the constant. And that forces distance and time to be relative, because if one is relative, then the other has to be relative. And so this breaks up this concept about simultaneity. Let's take a look at another version of this. Let's imagine that we have two aliens, Blip and Blorp. Blip is in a moving frame of reference, and the rocket ship is traveling with a velocity of v in this direction. And a short experiment is attempted. So there's going to be a pulse of light that originates at the floor of the rocket ship, and then a light pulse detector up here. So in Blip's frame of reference, the light's going to go off and it's going to travel in this path. And Blip is going to measure the time it takes for that to happen, for that event to happen. And that means that we'll call that time t0, and we'll call the length, the distance it travels, L. But Blorp sees the light travel from here to here, and also sees a spacecraft traveling from this point to this point. So this gives us a triangle, and we're going to blow up this triangle and take a closer look at it. So in this triangle, Blip's measurement and Blip's experiment, the light travels this distance, but to Blorp, who's in a stationary reference frame with respect to the starry background, Blorp sees a spaceship travel this far, and so that's going to be the speed of the spacecraft times the time that they measure. So Blorp measures time t. Blorp sees the light travel this distance, which is L0. And so that has to be the speed of light times the time that Blorp measures. So we have two different distances, and therefore we must also have two different times. Again, simultaneity doesn't exist when you're traveling close to the speed of light. So now we can simply apply the Pythagorean theorem. So that means that L0 is the hypotenuse, so we square that, and that's equal to L squared plus B times T squared. But then we can expand this out, and so L0 squared is going to be C squared times T squared, and C squared times T0 squared, and then B squared and T squared. So we can try and get all the t's to one side of the equation. And so that's going to become c squared times t squared minus b squared t squared. And, you know, I don't usually like just doing algebra for the sake of doing algebra, but the interesting thing is that this derivation is so short, it can actually be done on an index card. So now we're really close to finding a relationship between t and t0. Let's divide through by c squared and collect like terms. So t squared times 1 minus b squared over c squared is equal to, and now the c squareds have canceled out. So this is t0 squared. And now we take the square root of both sides, and we can see that we have a conversion factor that takes us back and forth between the time experienced in the moving frame and in the rest frame. And so this term underneath the radical is really like a correction factor, which is really the easiest way to think about it. And look at that. So it turns out that special relativity is really just common sense when you think about it. If everybody has to agree on the speed of light, then that means that time and distance are now relative. And also, everybody's going to agree about speeds. So L divided by T0 is going to be equal to the speed of the spaceship. And actually, that would be the speed of light. And L0 divided by T also has to be equal to the speed of light. So everybody's going to agree on those two things. So that's where this correction factor comes from. Let's spend a little bit of time thinking about what this number means. So first of all, nothing can travel faster than the speed of light. Otherwise, energy conservation breaks. And we can't have that. So if V will always be less than C, then this number will always be less than 1. And then 1 minus number less than 1 will also be a number less than 1. So this will be constrained to have a value between 0 and 1. So we'll go back to sharing our screen. And we can see now here is our correction factor. If we take a look at different values for V over C, we can see that as V approaches the speed of light, the correction factor gets really, really small. And if V was to be faster than the speed of light, we'd actually get an imaginary number for that. So again, that would break energy conservation. And then slower speeds, you know, at 1/100th the speed of light, or even 1/10 of the speed of light, the correction factor is pretty much just 1. So not that big of a deal. So our conclusion is that moving clocks run slower. And the same thing with distances. So the distances measured in the moving frame are going to appear to be shorter. That's called length contraction. And the other key components of momentum and mass will also be relativistic. And it's because as we pump energy into a system, when we get close to the speed of light, you can still add energy to the system, but it's going to behave as if it's got more mass. Right, and so then that's where E equals mc0 squared. This is the so-called rest energy. And it doesn't, because the speed of light is such a large number, that converting mass to energy releases a huge amount of energy. Great. So let's try a problem. In this example, let's plan a trip to the nearest star from our own solar system. And so let's go to Proxima Centauri. That's the nearest star to our own solar system, and it is 4.5 light years away. At least that's what we measure it to be. 4.5 light years. Which we can abbreviate as just 4.5 Ly. And let's select a speed that's relativistic. So let's suppose we're going to go at 90% of the speed of light. So 0.9 c. So let's see what our correction looks like. So we'll always do this first, figure out what our correction is. So that's going to be 1 minus v over c squared, and then take the square root. And you notice this correction doesn't have any units. Okay, so let's go ahead and give this a try. So what we want to do, we're doing 0.9 c over c, so the c's will cancel. So really this is 1 minus 0.9 squared. Okay, good. And then we want to take the square root of that. So when you take the square root of a number less than 1, you'll get a slightly bigger answer. So 0.43. Let's call it 0.44. That should be fine. Now, at this rate, in the time with respect to our starry background, it's going to look like this. So t is going to be equal to distance divided by the velocity. So our distance is 4.5 light years, and our velocity is 0.9 c. So when we do this division, speed of light and light, that's actually just going to cancel out. So it should take slightly longer than 4.5 years, because that's how long it takes light. 4.5 years is how long it takes light to reach us from Proxima Centauri. It's not really a star you can see with the naked eye. It's very faint, but it is the nearest star. Okay, so now let's figure out what that number is going to be. So 4.5 divided by 0.9. Okay, so our astronauts in training, and you know, everybody knows astronauts like pizza. So this gives us a rough idea. It's going to take us 5 years to get there at that speed. So we know how many frozen pizzas to put on their spaceship. Okay, great. Now let's go back and forth between, we know everything about the rest frame, that we measure the distance to be 4.5 years, and that the time is going to be 5 years in order to get there. So that's what's happening in the rest frame. So our distance is equal to 4.5 years, light years rather. And the time that it's going to take to get there is 5 years. And if we divide these two, then you're going to get 0.9. Now in a moving frame, let's see what happens. So we're going to have a distance L, which is going to be contracted to be smaller. And time moving clocks appear to run slower. So we're going to multiply our correction, 0.44 times the time in the rest frame, and 0.44 times our uncontracted distance. Okay. .44 times our original distance, which is 4.5 light years. And so our moving spaceship is going to measure the distance to only be 1.98 light years. That is length contraction. And moving clocks are going to run slower. So the astronauts are actually going to experience 2.2 years of aging instead of 5. Now notice if we divide these two, we said before, if we divide these two numbers together, we're going to get 0.9 C. And if we divide these two numbers together, let's see what we get. So 1.98 divided by 2.2. Yeah, we get 0.9. So everybody agrees on the speed. And this is the twin paradox then. So if we have two twins, one goes on the trip and one stays home, the twin who stays home is going to age 5 years, but the twin who's moving is only going to age 2.2. And if we repeat the same conditions coming back, it's going to be the same thing. So the twin who's in the rest frame will age 10 years, and the twin who is in the moving frame is only going to age 4.4. But again, you can see that this relativistic correction is just common sense, assuming, of course, that the speed of light has got to be the same. It's a property of the material. It's not a property of the thing that created the light. And that simple fact leads to the lack of simultaneity between the two reference frames. I hope this was helpful.